Welcome to our deep dive into learning to reweight examples for robust deep learning by Ren et al. This 2018 paper from the International Conference on Machine Learning
Right.
tackles this familiar problem.
Yeah.
How do we make deep neural networks
Yeah.
less susceptible to biases in their training data?
Yeah. The authors present this novel method called example reweighting
Hmm.
that kind of goes beyond simply minimizing training loss. Instead, it uses a meta-learning approach to learn how to assign different weights to training examples, guided by a small, clean validation set.
So the paper really highlights the limitations of traditional approaches when dealing with common biases like class imbalance and label noise.
Yeah, that's right. Think of an autonomous driving system being trained on a data set that's dominated by images of standard vehicles.
Right.
It might become overly confident in recognizing those while struggling with less frequent but critical cases like pedestrians or emergency vehicles.
Okay.
That's class imbalance in action.
Okay. And label noise, as we know, can be even more insidious, especially as data sets grow larger and labeling becomes less meticulous, like trying to learn from a textbook riddled with errors.
Exactly. And traditional methods, which often focus on minimizing training loss, run into a conflict. In the presence of noisy labels, you want to prioritize low-loss examples,
Right.
assuming they're clean. But with class imbalance, those high-loss examples might actually be the ones from the underrepresented class that need more attention.
So you're stuck in this dilemma of trusting low-loss examples while ensuring that minority classes aren't neglected. How does this paper propose to break free from this conundrum?
The key insight is the use of a clean, unbiased validation set as a guiding reference during training. This allows the model to distinguish between good and bad bias. Many real-world data sets naturally lend themselves to this setup, with a smaller, high-quality portion and a larger, more coarsely labeled one.
It's like having a trusted reference manual to cross-check against a potentially error-filled textbook. So how does meta-learning come into play here?
Meta-learning, in essence, is about learning how to learn.
Okay.
In this context, it's about learning the optimal way to weight training examples. Instead of computationally expensive optimization over the entire training set, the algorithm focuses on mini batches and cleverly analyzes the gradient directions of each example.
Gradient directions. Could you elaborate on their significance in this context?
So imagine the loss function as a complex, multi-dimensional landscape with hills and valleys.
Right.
The gradient direction at any point on this landscape indicates the direction of the steepest descent, the path of fastest improvement.
Okay.
This paper's method examines the gradient directions of each example on both the training loss and the validation loss.
So by analyzing the gradient directions with respect to both losses, the algorithm can identify which examples are truly helpful for generalization.
Precisely. Examples with similar gradient directions on both losses are likely to be beneficial and get upweighted.
Okay.
Conversely, those with opposite gradient directions, suggesting they might be leading the model astray,
Right.
get downweighted.
Okay.
This analysis is implemented efficiently using automatic differentiation,
Right.
a core technique in deep learning frameworks.
That's a clever way to leverage existing tools for a novel purpose. But how does this method actually perform in practice?
To test their method, the authors designed experiments using the MNIST and CFAR datasets,
Okay.
intentionally introducing both class imbalance and label noise.
The MNIST and CFAR datasets are kind of the go-to benchmarks for many computer vision tasks. Can you delve into the specifics of their experimental setup?
For MNIST, they focused on handwritten digit classification, creating an imbalance by deliberately overrepresenting certain digits.
Okay.
With CFAR, they introduced both uniform and what they call background flip label noise.
Interesting.
The latter simulates a realistic scenario where some images are mislabeled as belonging to a dominant background class.
These carefully crafted scenarios allow for a rigorous evaluation of the algorithm's ability to handle various forms of data bias. What were the key findings from these experiments?
The results were quite compelling. Across all these challenging scenarios, the proposed method consistently outperformed traditional techniques like AdaBoost and hard negative mining, achieving higher accuracy and demonstrating remarkable robustness even with significant noise levels.
That's impressive. It suggests that this approach could be a valuable tool for real-world applications where data biases are often unavoidable.
Absolutely. And perhaps the most striking finding was the significant impact of even a small, clean validation set.
Right.
It highlights this crucial principle that data quality, even in small amounts, can be more important than sheer quantity.
It's like having a small, trusted compass to navigate through a vast, potentially misleading data landscape. This begs the question, how exactly does the algorithm achieve such robust performance? What's going on under the hood?
Let's unpack the mechanics of the algorithm in more detail. We'll delve into how the example weights are calculated and explore the role of automatic differentiation in making this process efficient. So at the core of this method lies this clever manipulation of gradients during training. As you know, deep learning models rely on backpropagation to adjust their weights based on the gradients of the loss function. This algorithm leverages this process by analyzing the alignment of gradient directions calculated on both the training data and the clean validation data.
So instead of just looking at the magnitude of the gradient, it's about comparing the directions with respect to these two different data sets.
Precisely. For each example in a mini-batch, the algorithm examines the similarity between its gradient direction on the training loss and its direction on the validation loss. If these directions are aligned, it suggests that this particular example is contributing to the learning process in a way that's consistent with the validation set's notion of a good model.
Meaning, these examples are pushing the model towards a solution that generalizes well to the clean, unbiased data.
Exactly. These examples are then given a higher weight during training. On the other hand, if an example's gradient directions on the two losses are misaligned, or even pointing in opposite directions, it's a sign that this example might be leading the model astray due to biases present in the training data.
So the algorithm effectively downweights these potentially harmful examples. It's almost like it's learning to filter out the noise and focus on the true signal.
That's a great way to put it. And this process of comparing gradient directions and adjusting example weights happens dynamically during each training iteration, creating a feedback loop that guides the model towards a solution that not only minimizes the training loss, but also generalizes well to the clean data.
This dynamic weighting scheme seems like a powerful way to mitigate the effects of data bias. Can you elaborate on how these example weights are actually calculated?
The paper provides a specific example of weight calculation in the context of a multi-layer perceptron network,
Okay.
or MLP network, as you know.
Okay.
During backpropagation in an MLP, gradients are calculated layer by layer, propagating error signals backward through the network.
Right, and these gradients are used to update the weights of the connections between neurons in the network.
Precisely. Now, in this reweighting algorithm, the crucial step involves calculating the gradients of the validation loss with respect to the example weights.
Okay.
This calculation involves computing dot products between the activations of a training example and the activations of a validation example at each layer.
So we're measuring the similarity between a training example and a validation example in terms of their activations throughout the network.
Yes, additionally, we compute dot products between their corresponding gradient directions at each layer, capturing how much they individually influence the learning process.
Interesting. So by combining these dot products across all layers, the algorithm determines the final weight assigned to each training example.
Exactly, and the beauty of it is that this seemingly complex process can be implemented quite efficiently using automatic differentiation. This allows the reweighting algorithm to be seamlessly integrated into existing deep learning frameworks, like TensorFlow or PyTorch.
Automatic differentiation really is a game changer for these kinds of sophisticated calculations. It frees us from the tedium of manual gradient calculations, allowing us to focus on the higher-level algorithmic design.
Absolutely, but the authors don't stop at just presenting a clever algorithm. They also provide a theoretical analysis of its convergence properties.
Yep.
They show that under certain conditions, their reweighted training process converges to a critical point of the validation loss function.
That's reassuring. It provides a mathematical foundation for the algorithm's effectiveness, showing that it's not just a heuristic, but a method grounded in sound principles.
Indeed, and importantly, this analysis highlights that while the algorithm uses information from both the training and validation sets, it ultimately aligns itself with the distribution favored by the clean, unbiased validation set.
So the validation set acts as a guiding light, steering the model towards a solution that generalizes well, even when the training data is trying to pull it in a different direction due to inherent biases.
Precisely. Now let's revisit those experimental results on NNIST and CIFAR and delve deeper into the specifics of how this method performed against traditional approaches. So let's dive back into those experiments. The paper presents some compelling visualizations, particularly in Figure 3, that really bring the algorithm's performance to life.
Okay.
Figure 3 beautifully illustrates the algorithm's ability to differentiate between clean and noisy examples. The heat map visualization shows how the algorithm effectively assigns lower weights to those examples identified as noisy, represented by cooler colors.
It's striking how the algorithm, guided by the validation set and the gradient information, learns to identify and downweight these potentially misleading examples.
Yes, and on the right side of Figure 3, where the focus is on examples from a single class with background noise, we see how the algorithm correctly picks out the clean examples and assigns them higher weights.
It's almost like the algorithm develops an eye for clean data, effectively filtering out the noise and focusing on the signal that leads to better generalization.
That's a great analogy. The paper also highlights the algorithm's robustness to overfitting, a common challenge when dealing with noisy labels. Traditional methods often show a degradation in validation accuracy as training progresses, especially after learning rate decays.
Right, because the model starts to overfit to the noise in the training data, sacrificing its ability to generalize to unseen examples.
Exactly. But the meta-learning algorithm, due to its reliance on the clean validation set, maintains a steady course, consistently aligning itself with the validation set's feedback and avoiding this overfitting pitfall. The training curves presented in the paper clearly demonstrate this stability.
So it's not just about achieving higher accuracy, it's about achieving it in a more stable and reliable way. This robustness is crucial for real-world applications, where we need confidence that our models won't suddenly become unreliable due to overfitting to noise.
Absolutely. This paper's findings offer a significant contribution to the field of robust deep learning. By combining the principles of meta-learning with the guidance of a clean validation set, this method effectively tackles the challenges of data bias, leading to models that are not only more accurate but also more reliable and trustworthy.
To wrap things up, could you summarize the key takeaways from our deep dive into this research?
This paper presents a novel approach to example reweighting that leverages meta-learning and a small, clean validation set to mitigate the impact of data biases on deep learning models. The algorithm cleverly analyzes the gradient directions of examples with respect to both the training and validation losses, dynamically adjusting their weights during training to promote generalization. The experimental results on MNIST and the CFAR, particularly the visualizations of example weights and the stable training curves, demonstrate the effectiveness and robustness of this method, showcasing its potential for real-world applications where data biases are often inevitable.
Thank you for joining us on this deep dive into learning to reweight examples for robust deep learning. It's been a fascinating exploration of a method that holds great promise for building more robust and reliable AI systems.